So a type 1 error is the mistake of rejecting the null hypothesis when it is actually true. A type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. The probability of a type 1 error, we use alpha for that. The probability of a type 2 error, we use beta. Okay. And that's really the last important topic that's covered in 8.2. Here's a nice little table here that kind of summarizes everything. This says we decide to reject the null hypothesis. The null hypothesis is true, but if we rejected the null hypothesis, that's a type 1 error. If we decide to reject the null hypothesis and the null hypothesis is false, then we made the correct decision. And hopefully that's what we would do most of the time. If we fail to reject the null hypothesis and the null hypothesis is true, then we made the correct decision. If we fail to reject the null hypothesis but the null hypothesis is actually false, then that's a type 2 error. Okay. So that is the end of 8.2. There's still a lot of good stuff about type 1 and type 2 errors and this power of a hypothesis test. I mean, it's definitely worth reading, but it's not something that we're going to get into. Alright, so let's see if we can look at a few of these problems. So in these problems, find the value of the test statistic. So how about we look at problem number 16 here. Alright. Claim for adult females, the mean of their white blood cell counts is equal to 8.00. The random sample of 40 adult females in dataset 1 from Appendix B has white blood cell counts with a mean of 7.15 and a standard deviation of 2.28. The population standard deviation is not known. So why is that so important, that the population standard deviation is not known? Well, we have to figure out which test statistic to use. You're going to use the test statistic according to the parameter that we're talking about. Is it a proportion? Is it a mean? Or is it a standard deviation? Okay. I see a lot of numbers up here. You know, what do they all mean? Look at the claim. The claim says the mean of their white blood cell counts is equal to 8.00. So we're talking about a mean. Now we're not going to go through and solve this claim or try to figure out this claim. We more than likely do not have enough information. This section is just practicing on finding the test statistic. So if we're talking about a mean, then either look at your formula sheet or look back where we were talking about when we were looking at the table that shows all the test statistics. All right, this one right here. So if we're talking about a mean, then it's one of these two test statistics. What's the difference? If the standard deviation, the population standard deviation is known, then it is a z distribution. If the standard deviation is unknown, then it is the t distribution. So, did our problem say it was known or unknown?
Not known.
It's not known. So that means this is a t distribution. Some people call it a student t distribution.
What page is that table?
In your ebook, that table is 387. Okay, so we do not know the standard deviation, the population standard deviation, and we're talking about a mean, so it's a t distribution. So this is the test statistic that we use. Okay, so we have, this is for problem number 16, t equals x bar minus mu over s divided by the square root of n. Okay? Well, I guess I'm going to be able to resize it. Okay? So, the x bar, remember, that comes from a sample. S comes from a sample. That's a sample standard deviation. N, of course, that's from the sample. The only thing we need is a population mean. Okay? So, here's the claim. That's our mu. White blood cell count is equal to 8.00. So that's mu. Random sample of 40 adult females. What is that? N. Now then it starts talking about data set 1. So this is from a study, the data set 1 is. Mean of 7.15. What is that? X bar. And a standard deviation of 2.28. So what is that? S. Okay. So we plug those into our formula. And we have 7.15 minus 8 over 2.28 divided by the square root of, what was our n? 40. Okay? So I would suggest, you never want to round anything if you don't have to. We won't round until the end. What I'd suggest doing is maybe working the numerator out first. So that's 7.15 minus 8. So my numerator is negative 0.85. Then what we can do is work out the denominator. Okay, and so I could say 2.28 divided by the square root of 40 equals, so this is what the denominator is equal to, and that's a long number, right? So there's a couple ways you could do this now. you could either say the inverse of this times negative 0.85, or you could type in negative 0.85 and divide by this. So, like I said, different ways you can do it, but you want to make sure that you get the right answer. The reason why we could take the inverse of this is because if we had this decimal down here, you've always hopefully been taught that if you have something in a denominator and you want it to move it to the numerator, you can just put it over 1 and flip it and multiply. So that's what we would be doing if I took the inverse, the 1 over x right here. Alright, so I got negative 2.35783. If you do have a chance to use a calculator like this, then another thing that you could do is you could just type all this in and use parentheses. Like I could say parentheses 7.15 minus 8 parentheses, and say divided by, open parentheses again, 2.28 divided by 40 square root, and then close parentheses and hit equals. And you see I get the same answer, negative 2.3578 whatever. Okay, and so this is our test statistic. We want to round test statistics to 2 places or 3 places, depending on, usually that's what the problem would ask, 2 or 3 places. So, you know, since we have a lot of big numbers in here, I'll just round it to 3 places. Negative 2.358. Okay. So now, you want to do another test statistic? Of course, you do. All right, let's go up to number 14. I'll leave the odd ones for you because you can check those answers in the back of the book if you need to. Alright, so let's look at number 14. Tax returns. Claim, among those who file tax returns, less than 1/2 file them through an accountant or other tax professional. Less than 1/2. Okay. A fellow survey of 1,002 people who file tax returns showed that 48% of them file through an accountant or other tax professional. Alright, so we want to figure out the test statistic. We have to figure out what type of test statistic. And this is a less than 1/2. 1/2 is a probability, I'm sorry, a proportion, isn't it? A fraction. Less than 1/2. That's a proportion. So P is less than 1/2. That was the original claim. So we need a test statistic for a proportion. So if you go back and look at your chart for a proportion, we use Z equals P hat minus P over the square root of PQ over N. Alright, and so how about we practice on this one also, writing the original claim and figuring out the null and alternate hypothesis. So here was the original claim. less than half. So you write the opposite of that. That would be greater than or equal to 1/2. Now the one that has equality is the null hypothesis. So the null hypothesis is P equals 1/2. And the alternate hypothesis is P is less than 1/2. The one that has equality, you make it equals. The other one will be your alternate hypothesis. Alright, so this value here, 1/2, is my P. P hat will come from the sample. We'll have to figure that out. And then if P is 1/2, Q is 1/2, and then we'll have to figure out the N, whatever the number of data items are in the sample. Okay? So a survey of 1,002 people. So your N is 1,002. And then it showed that 48%. So that's your point estimate, P hat, 0.48. Alright, so P hat is 0.48. P is 1/2 or 0.5. Q is 1/2 or 0.5. And N is 1,002. All right. So my test statistic is equal to 0.48 minus 0.5 over the square root of 0.5 times 0.5 over 1,002. Alright, let's see if I can put all this in parentheses now. The square root of I messed something up. So 0.5 times 0.5 divided by 1,002 square root. It should follow the order of operations. Hopefully left to right. There. Alright. I got, if I round that to 3 places, negative 1.266. Okay. So hopefully we're a little bit better at figuring out the test statistic, and hopefully we're a little bit better if we did have to find the null and alternate hypothesis, which we do when we do a hypothesis test. We also practice that a little bit. There are some more of those 5 through 8 if you need some more practice stating the null and alternate hypothesis. Okay. Let's see if there's any more good things here. Finding p-values and critical values. Since there's 2 different types of ways, we should probably practice that a little bit. This says, assume that the significance level is alpha equals 0.05. Use the given statement and the p-value. Use the given statement to find the p-value and critical values. Alright, so how about we do some of the even ones? So I'll do number 18. Let's look at that one. A test statistic of z equals negative 2.00 is obtained when testing the claim that p is less than 0.5. Okay, so we're using a significance level of 0.05. So we want to find the p-value and we want to find the critical value. Now, we don't have a test where we use both of those. Just know that we're finding this. The p-value is used with one test and the critical value is used with a different test. But it does ask us to find both so we can practice. Alright, so the way that we figure out the p-value, let's do that first. For the p-value, we need to know, and I'll make a copy of that there real quick. For the p-value, what do we need to know? We need to know, is the test left-tailed, right-tailed, or two-tailed? Okay? So once we know that, then we can use this figure here to help us calculate the p-value. The way that we tell if a test is left-tailed, right-tailed, or two-tailed is by looking at the alternate hypothesis. Now, we weren't given the alternate hypothesis, so we have to figure out the alternate hypothesis. It tells us that the claim was p is less than 0.5. So the opposite of that is p is greater than or equal to 0.5. The one with equality, that's going to be our null hypothesis. So the null hypothesis is p equals 0.5. We always put equals with the null hypothesis. The alternate hypothesis is the other, whatever didn't have equality. So it's p is less than 0.5. All right. So the alternate hypothesis tells us whether the test, whether our test is left-tailed, right-tailed, or two-tailed. Since the alternate hypothesis was less than, this is a left-tailed test. Less than left-tailed. Greater than right-tailed. Not equal to is two-tailed. So this one is left-tailed. So what does that tell us? That tells us that our p-value is equal to the area to the left of the test statistic. All right, area to the left of the test statistic. So our test statistic was given as z equals negative 2.00. All right, so we want to know if this was under a bell curve. This was like this. We had our bell curve with all of our data. It's left-tailed, so somewhere over here we have a z of negative 2.00. We want to know, what is this right here? And then our p-value is going to be the area of that region. So since this is a z distribution, we use the z table. All right, that's in Appendix A. And our test statistic was negative 2.00. Negative 2.00. All right, so that means that our p-value is 0.0228. So our p-value 0.0228. All right, now let's find our critical value. The critical value comes from the actual significance level. Our significance level is 0.05. All right. Now, was this test left-tailed, right-tailed, or two-tailed? It was left-tailed. So that means that area of 0.05, we want that to be in the left tail. We don't divide it by 2 like we did in the last chapter because it's not two-tailed. If it was two-tailed, we would divide it by 2. But it's one-tailed. It's left-tailed. So we need an area of 0.05. So we want to get as close as possible to 0.05 as an area in our z-table. So 0.05 is right here. That's negative 1.6. And then if you were to go down and follow that arrow, negative 1.645. All right, so the critical value is negative 1.645. Okay. Now, just as a little extra added bonus to this problem, you will not be charged extra for this. I'm going to show you, would we reject or fail to reject this claim with each of these? And we should get the same answer for both of them. Okay? So, the p-value method to figure out whether you want to reject H sub O or fail to reject H sub O. For the p-value method, you look at the p-value and you look at the significance level. If the p-value is greater than the significance level, then what does that mean? That means that we fail to reject the null hypothesis. If the p-value is less than the significance level, then you reject the null hypothesis. So, is this greater than or is this less than 0.05? 0.02 is less than 0.05. So that means we need to do what? If you don't remember, it's in a table in your text. I can show it to you real quick. To make sure you got that down pat. Alright, and I told you if your text has a slash right here, this is supposed to be a greater than symbol. That's only in the ebook. For some reason, the ebook through VitalSource right now has a slash instead of a greater than. But if the p-value is less than alpha, it's less than the significance level, reject. Go back to our problem. 0.02 is less than 0.05. So we reject H sub O. Okay? Now, the way that and so that's how we would figure out if we reject or fail to reject using p-value. The way that we figure that out using the critical value I have this same collection of data under here. Somewhere right here is my test statistic, right? We figured out Z was negative, well, it told us, the problem told us Z is negative 2.00. We all understand how positive and negative values work, right? The further you get to the left, the what? It'll be the bigger the number, but it's actually smaller, right? Now, here's the test statistic. Here's the critical value. So, does the test statistic lie in the critical region? Or does the critical value lie in the test statistic? It's either one of the two. Okay. If the test statistic is in the critical region, reject H sub O. If the test statistic is not in the critical region, fail to reject H sub O. Okay. So, the critical region, this negative number would be on this side. Remember, because negative numbers, the number itself gets larger as you go to the left. It's actually smaller, but it gets larger. So if my critical value is right here, the test statistic is in that critical region. Okay?
Critical region is on the other side of it.
The critical region is from the critical value to the left. And the the test statistic, negative 2.00, would be inside the critical region. This is the critical value. It's where the critical region starts. And then the test statistic is negative 2, would be inside that critical region. So again, we would reject H sub O. Either test gives you the same thing. To me, you don't have to draw a graph to do the p-value method. So when you can use the p-value method, you probably want to use the p-value method. But since with the critical values, especially if it's left-tailed, the negatives sometimes will kind of play tricks with your mind. You'll be thinking, well, negative 2 can't be in that critical region because negative 2 is greater than negative 1.6. But it's not. It's actually less than negative 1.645. So only use the critical value method like when you have to. And we'll have to if it's t-distribution or if it's standard deviation, which would be the chi-square distribution type problems. Because you have to have technology to find the p-value with those. The formula is way too complex to learn. Alright, so that's how you find a p-value and the critical value. And we will definitely have more practice testing the hypothesis. Let's do one more. Find the p-value and find the critical value. Alright, so let's look at number 20. The test statistic Z equals 1.50 is obtained when testing the claim that P is not equal to 0.25. Alright, so we have, this is our test statistic that's given to us. And then the claim, the original claim is P is not equal to 0.25. The opposite of that is P equals 0.25. So the one with equality, that is our null hypothesis. The other one is our alternate hypothesis. We need the alternate hypothesis to tell us if it's left-tailed, right-tailed, or two-tailed. This thing is two-tailed. So we have a critical region on both sides. All right, so that means since this is two-tailed, all right, we use the same significance level for this problem. All right, let's first find the p-value. Then we'll find the critical value. All right, the p-value test, remember you want to use that figure. First you figure out, is it left-tailed, right-tailed, or two-tailed? This is two-tailed. So we're in the middle of that figure. Then it says, is the test statistic to the right or to the left of the center? If the test statistic is positive, that means it's on the right side. If it's negative, it's on the left side. So since it's positive, follow your figure on the positive side. It says that we want the p-value is the area twice to the right of the test statistic. So I don't have to draw this graph, but I will for the p-value, just to kind of reiterate. It's two-tailed, so you have two critical regions, and our test statistic is positive. So our test statistic is on the right side of our bell curve. So since it's two-tailed on the right side, we want the area to the right so that we can say twice that. That's going to be what the p-value is, because it's actually this and this. So that's why we have to say twice that. All right. If we use our z-table, how can we figure out what this shaded region is? We're going to have to use our z-table and then say 1 minus what we get in our z-table, because it's right-tailed. Remember, the z-table shows the area cumulative from left to right. So if I look at my table, I go to a positive 1.50. Remember, the area is cumulative. That's why it gives me this big decimal so close to 1. 0.9332. So it's 1 minus 0.9332 gives me the area for this little region here. 0.0668. The p-value, since this was two-tailed, is twice that. So my p-value is 0.1336. My critical value I'm going to get from my alpha. Now, how does this differ, finding the critical value, than the previous problem? On the previous problem, we were left-tailed, so we only had one critical region. And since we were left-tailed, to find that critical region, we just used 0.05. On this problem, we're two-tailed. So to find the critical region, we're going to have two critical values. We're going to have one over here on the left side and one over here on the right side. So for the critical value, we want both of these areas to add up to be what? 0.05. So that means since it's two-tailed, we have to say 0.05 divided by 2. So we want an area of 0.025 on each side. Alright, so we're going to have a positive and a negative critical value. So what you can do though, since this is a z distribution, remember we have symmetry. If we find the negative one, then we can just take the opposite sign of that and that'll give us the positive one. Okay, so that's the quickest way. So if you want to find this one on the left side, look in your table for an area of 0.025. Alright, so decimal 0.2 and that's as close as we can get. 0.0256. That's a z-score of negative 1.95. Let's look. Just check the box down here. See if there's any special value. No, they're not. They don't give us a special value. So (0.0256) negative 1.95. Yes.
The one to the right of it is exactly that.
Okay.
Negative 1.56.
So if we look at the one on the right, let's look at that little table down there, see if there's something on the right.
No.
Back up.
Negative 1.96. Unless I'm looking at the wrong
Negative 1.96. Let's see. I wish I had it in front of me. It's hard to tell. Oh, okay. Yeah, that was 0.256. 0.0250. So negative 1.96. Usually that's in a table somewhere, so they must have taken it off the table at the bottom. But that's what we needed, 0.025. So the negative answer there, negative 1.96, is one critical value. The other critical value is going to be the positive 1.96. And so, would we reject or fail to reject? If we look at our p-value, the p-value is larger than the significance level. Since the p-value is larger than the significance level, we failed to reject H sub O. Let's see if we would get the same answer if we used the critical value method. So we want to use the side where our test statistic is. The test statistic is on the right side. So our critical value on the right side was 1.96. So everything to the right of 1.96 is in the critical region. Our test statistic was 1.50. If you think about this like a number line where this is 0, is 1.5 going to be in there? No, because the numbers to the right are larger. So since it's not in there, you fail to reject H sub O.